Okay, today we are going to start the fourth module. In fourth module, we will discuss partial differential equation, higher order partial differential equations, and how to solve some special type of partial differential equations. Okay, കേൾക്കാവോ ഞാൻ പറയണത്? ഓക്കെ അല്ലേ? Okay. So yes. So this is the general form of a second order linear PDE. Okay, so we are trying to solve PDEs of this form. Okay. In general, there is no method for solving all the partial differential equations. There is no general method for solving all the partial differential equations. Okay. Even this is a special type of partial differential equation. This is not a general partial differential equation. This is a special type of second order partial differential equation. Okay, we know what is partial derivative. Okay, if a function, suppose z is a function of xy, then we know what is partial derivatives. Okay, we write the partial derivatives I like dou z by dou x or zx. Okay, we will write like this, or simply fx. All are representations of the partial derivative with respect to x. And what is the meaning of partial derivative? Partial derivative means it is a derivative of given function with respect to that single variable. Okay, so this fx stands for derivative of this whole function with respect to single variable x, treating other variables are constant. Okay, here is a function of two variables, so we have only one other we have only one extra variable, that is y. Similarly, we can define the partial derivative of this function with respect to y. Okay, and also that they are the first order derivative. They are called the first order derivative. So zx and zy are the first order derivatives. Okay, similarly we can define higher order derivatives, especially that is called second order derivative. For example, dou square z by dou x square. Okay, and dou square z by dou y square. And what is the meaning of dou square z by dou x square? Or simply we write this as zxx. Okay, so zxx, or you can write fxx. All are the notations of the same concept. The second order derivative dou square z by dou x square means we have to differentiate z partially with respect to x two times. First we will differentiate z with respect to x, then again we differentiate that derivative with respect to again x. Okay, because derivative is also a function of x. You got it? Similarly, we can define zxy. What is zxy? Zxy means we differentiate z with respect to x and y. Okay, in general, but in case of practical applications, these two derivatives are same. Here zxy stands for, suppose first we differentiate with respect to y, then you will differentiate with respect to x. Zyx means first you differentiate with respect to x, then differentiate with respect to y. Okay, in general they are not equal. In general, at least in theoretical interest, they are not equal, but in our practical situations they are always same. So that's why in our study we assume that they are same. These two derivatives are same. Whatever the order of differentiation, the value is same. Okay, most of the cases they are same. But there are some theoretical examples such that these type of derivatives are not equal. Okay, we are not interested on such examples. Okay, we will assume that they are same. That are the things about partial derivative. I think all of you familiar with what is the partial derivative and what is the geometry of partial derivative, such things in, I think, beta classes. Okay, so okay, so anyway, this is our we are interested on to solve this type of partial differential equation. This is linear because there is no square term is there, no square or any power. There is no power term. For example, you consider a partial differential equation like this: uxx square plus uy equal to 0. This is a partial differential equation, second order partial differential equation, but this is not linear because here one term contains a power term. Okay, square is there, or okay, so here all the powers are units. Okay, there is no product term like this. Suppose a partial differential like this: ux uy plus some sin x is equal to 0. This is a PDE. This is a PDE, first order PDE, because it involves only first order derivatives ux and uy, but it is not linear because there is a product of u terms. You got it? So anyway, our general form of second order linear PD is this one: A times uxx plus B uxy C uyy plus D ux plus EUY plus FU equal to G, where A, B, C, D, E, F, G are functions of x and y. Okay, that means A may be function of any function of xy. Maybe A may be some x square y, possible. Okay, B may be e raised to xy, no problem. Okay, in general, A, B, C, D are functions of x and y. You got it? So this is the general form of second order linear PD. Okay, so why we are actually we are going to discuss what is canonical form of the second order PD. Why we are going to discuss canonical form and all. Actually, our ultimate aim is to solve a PD, because there are so many PDs arising from the practical situations. The familiar one is heat equation and wave equation. Okay, heat equation and wave equation are second order partial differential equations. They are arising from practical situation. Okay, our aim is to solve a physical problem. Our aim is to solve a physical problem. To solve, suppose we have a physical problem, then corresponding to this physical problem, we construct or we find an equivalent, almost equivalent, a mathematical problem. This process is called mathematical modeling. This process is called mathematical modeling. Finding a mathematical equation or mathematical structure corresponding to a physical problem. This process is called mathematical modeling. Okay, so there are so many PDEs arising from physical situations. So our aim is to find an efficient method to solve all the PDEs. Unfortunately, there is no such method to solve all the PDEs. Okay, so we are trying to solve a particular class of problem. This is a special class of problem. These type of problems are called second order linear PDE. Okay, but unfortunately there is no general method for solving such simple, I think it's a very simple representation. Okay, so there is no general method. There is no general method for solving these type of PDEs, even these type of PDEs. Okay, so what we'll do? So some PDEs are very easy to solve. Some second order linear PDEs are very easy to solve, but in general there is no method. So that's why we find a method that is called okay. In this method, our aim is to, suppose this is our given PD. Let it be some space X. So this space X contains set of all second order linear PDs. Okay, but okay, we will, okay, in this method, a canonical form means corresponding to this PD, we will find another PD. Okay, that is the idea of canonical form. So canonical form is like a transformation. We find this is a given PD, like a PD like this in xy domain, in xy domain. Okay, so in the canonical method means we are going to find a new PD. This is a new PD in another domain. Let it be psi and eta. We choose two variables are psi and eta. Okay, this is another space. So let it be capital Y. Okay, and this new PDE is called the canonical form of this old PDE. So old PDE is in terms of x and y. Anyway, some independent variables x and y. Then we are going to find an equivalent PDE which is in another variable psi and eta. Okay, this psi and eta are a new transformation. Okay, then we expect this PDE is much simpler than this one, or maybe this PDE is solvable. Suppose this PDE is not solvable. Maybe the equivalent PDE in other two variables psi and eta may be solvable. Okay, then we find the solution of this PDE. Then using this solution, we can find the solution of this original PDE. Okay, this is the rough idea of canonical form. So this PDE is called canonical form. Okay, this is called canonical form. You got the idea? So we have a PDE. Suppose it is not solvable, then we find a new PDE in two new variables. That is called the canonical form. Sometimes this not in general. Sometimes this canonical form is solvable. Sometimes this canonical form is much simpler than this one, and it is solvable. Then we solve this canonical form. Using this solution, we find the solution of this original PDE. Okay, so that is the one advantage of canonical form. So in this session, we are going to find how to find the canonical form of a given PD and how to solve this new PD. Okay. So before going to find the canonical form, we have to define some technical terms. Uh, the first one is discriminant. What is discriminant? This is almost similar to our algebraic equations, b square minus 4ac. One thing is here b, a, b, c, everything are functions of xy. Maybe the constants, in general, they are functions of xy. That's why I'm using here delta of xy, because delta may be a function of xy. Okay. Anyway, discriminant is defined like this: b square minus 4ac. It is similar to our algebraic equations. Okay, and these are the three types of classification for PD, given PD. So if delta is positive, then this PD is called hyperbolic. If it is 0, then parabolic. It is less than 0, then it is called elliptic. Okay, so we have three type of PDs. Okay, and one interesting thing is the behavior of PDE may be different with respect to the point. Maybe in first quadrant, okay, this is x and this is y. Okay, x and y are dependent. U is a dependent variable. Clear? So maybe this one, equation number 1, may be hyperbolic in the first quadrant. Okay, maybe on this quadrant, this may be parabolic. Okay, because delta is not a constant, delta is a function of xy. So delta may be positive, negative, whatever be depending on the choice of xy. Okay, so behavior of this given PDE may be different in each of the quadrant or each depending on the points. Okay, anyway, we have three type of PDs. Then next we are going to define the canonical form. Before going to the canonical form, we are going to define the characteristic equations of the given PDE. The characteristic equations are given by this formula. Okay, by solving this equation, we get characteristic equations. And delta is nothing, our discriminant. Okay, so we have three cases because we have three type of discriminants are there. We have three type of discriminants are there: hyperbolic, parabolic, and elliptic. Okay, depending on the nature of delta, this right hand side may be suppose think about this one. Hyperbolic means delta is positive, parabolic means delta is 0, elliptic means delta is negative. Suppose the case is hyperbolic, then what happened? If it is hyperbolic, what about root delta? If it is hyperbolic, then we know that delta is positive. Delta is positive means positive square root is exist. This square root is exist. The real number, so its square root exists. So it is clear that we have two distinct equations: b equal to b plus square root of delta by 2a and dy by dx is equal to b minus square root of delta by 2a. We have two equations. Okay, corresponding to these two equations, we have two characteristic equations. Okay, when suppose it is a case is parabolic, what happened? If it is parabolic, then we know that delta is 0. Delta is 0 means what? What about the number of characteristic equations? What about the number of characteristic equations when the differential equation is parabolic?
One.
Yeah, only one, because if delta is 0, this time is 0. So b plus 0, b minus 0, both are same. So we have only one characteristic. In the case of hyperbolic, we have two. And one more interesting thing is this is a real number. This is a real valued function. If delta is positive, then its square root is also real. So we have two real characteristic. Okay, real characteristic. The one real characteristic. Okay, in last case, suppose our differential equation is elliptic. If it is elliptic, then we know that its delta is negative. If delta is negative, what about the square root of delta? That become real or complex? If
Complex.
yeah, delta is a complex number. Since delta is a complex number means we have two different complex characteristics. Okay, So in the case of hyperbolic function, we have two real characteristics. In the case of parabolic function, we have one real characteristic. In the case of elliptic function, we have two complex characteristics. Okay, with the help of this characteristic, we define two new functions, psi and eta. Okay, our aim is to find, I already mentioned, our aim is we have a domain of PDEs with the independent variables x and y, and we are trying to find an equivalent PDE. This is our given PDE in x and y. We are trying to find a PDE in new variable psi and eta. You got it? We are trying to find an equivalent PDE in other two variables psi and eta. So what is the relation between psi, eta and x and y? Naturally, there is a relation between psi, eta and x and y, because actually our PDE depends x and y. We have to find the new PDE with respect to other two variables. So naturally, there is a relation between these two variables, these two set of variables x, y and psi and eta. Okay, so our main task, our main first task is to find these two good relations, to transform to get a good PDE. Okay, so if it is hyperbolic, it is very easy. Hyperbolic and elliptic, then we have straightforward methods to find psi and eta. If it is parabolic, there is some trick. Okay, so if it is hyperbolic or elliptic, then we have straightforward method to find this psi and eta, the transformation function. Using this transformation, we have to find the new PDE. Okay, in the case of parabolic, we will use a small technique to find this one transformation. One is straightforward, other is we use some small trick. Okay, so anyway, I will explain how to find this psi and eta if the given PDE is hyperbolic, parabolic or elliptic with the help of some examples. Okay. Anyway, this psi and eta is almost given by these characteristic equations. Okay, actually we will find this psi and eta from solving this characteristic equation. I will show you how to find this psi and eta. Okay. So anyway, suppose there are two transformations psi and eta. They are functions of x and y. Okay. And one interesting thing is these two transformations should be independent. Okay, independent means what? Independent means one of them is not a multiple of other. That's all. One of them is not a scalar multiple of other. For example, psi equal to x plus y. Okay, then suppose eta equal to x minus y. Is it independent? Is it independent? Yeah, they are independent, because dependent means if in the case of two vectors, in the case of two functions, one of them is they are dependent only when one of them is a scalar multiple of other. Scalar multiple of other means a number times something. For example, in this case they are linearly independent. Suppose we choose psi as like this and eta as some 6 times x plus y. Then they are not independent, because here psi is x plus y, eta is 6 times x plus y. So they are not independent. Okay, but here they are independent. Or we have another technique to find they are independent or not. This is the simplest technique. This is a very simplest technique. You just simply check whether they are scalar multiple of one or not. That's all. Okay. Other mathematical technique is you find the Jacobian and check whether the Jacobian is 0 or not. Jacobian is nothing. Jacobian is like this: psi x, psi y, eta x, eta y, and check whether if determinant is not equal to 0, then linearly independent. If throughout 0, then dependent. Okay. One way of checking they are independent or not, you just find the Jacobian. Jacobian means determinant of psi x, psi y, eta x, eta y, and check whether determinant is not equal to 0. If determinant is not equal to 0, then independent, otherwise dependent. Okay. The simplest method is you simply check whether one of them is scalar multiple of other or not. Okay, one more question. Suppose psi is equal to x minus y and eta equal to x square minus xy. Is it independent or not? Is it independent or not?
Not independent.
Not independent, because here eta equal to x times x minus y, but this is not a scalar. This is a function. Okay, if it is a scalar, then it is no, it is independent, not independent the level. Okay, yeah, actually this is independent because here eta is equal to x times x minus y. Okay, this is not a scalar. If it is scalar, then not independent. So in this case, this psi and eta are linearly independent, no doubt. You can check the Jacobian. Okay, if it is a scalar, then not independent. Okay, this is not a scalar, this is a function, so they are linearly independent. I think you got the concept of scalar multiple or not. Our concept is clear. Anyway, this is the idea. Okay, then next, how to find the canonical form. Before moving to the canonical form, okay, now we have a given PDE. Now we have a given PDE and its characteristics. By solving the characteristic, suppose we have two reversible transformations, psi equal to psi xy and eta equal to eta of xy. Using these two transformations, we are going to convert. Using these two transformations, we are going to convert the given PDE to a new PDE. New PDE in new two variables. Okay, so actually what is the process of conversion? The process is very simple. That is using our chain rule. Okay, that is using chain rule. Actually the underlying theory is like that. Just full explain. I will just explain what is the underlying theory. How to convert this given PDE in terms of psi and eta. Because we have a relation like this. Maybe this psi equal to x plus y and sometimes eta equal to maybe some x minus y. So that's the idea. So psi is equal to function of xy and eta also a function of x and y. That's it. Like maybe like this, eta equal to x plus y or eta equal to x minus y, like that. Okay, then how to convert this PDE in terms of psi and eta? Okay, the one method is, first we are going to evaluate this ux, uy, uxx, uxy, uyy, everything in terms of psi and eta. Then we substitute all these things in this equation 1. By simplifying, we get a function in terms of psi and eta. We get a PDE. Okay, for example, how to find ux? How to find ux in terms of psi and eta? That is using our chain rule. Okay, we know that u depends psi and eta. We know that u depends psi and eta. And what about psi and eta? Psi and eta depends x and y. You got it? Psi and eta depends x and y. Okay, so what is our chain rule? How to find ux? How to find ux using chain rule? First you differentiate u with respect to psi, then you differentiate psi with respect to x, plus you differentiate u with respect to eta into eta with respect to x. You got it? So how to differentiate? What is the chain rule? So using chain rule, ux is nothing. Ux is u psi into psi x plus u eta into eta x. This is the chain rule. Now what happened? Now ux is in terms of u psi and u eta. You got it? Now ux is in terms of u psi and u eta. And what about psi x and eta x? We can evaluate psi x using the given formula, because this psi of xy is known. So you can evaluate the psi x from the given function. Similarly, you can evaluate eta x from the given function. So now this ux is completely in terms of psi and eta. You got it? Then we substitute this ux using this formula. Similarly, you can find uy, uxx, everything in terms of psi and eta, then substitute in 1. Okay, that is the idea of converting the given PDE in new PDE. Okay, actually this is a lengthy process. This is not a complicated process. This is a lengthy process. So I will give you a shortcut formula. After all the substitution and simplification, we get a new thing. That is the form. This is the form of the PDE. After finding this u psi, u eta, u psi, u psi eta, everything, and substituting and simplifying, we get a new PDE like this: A1 u psi psi plus B1 u psi eta plus C1 u eta eta plus D1 u psi plus E1 u eta plus Fu equal to G. Okay, and what are the constants A1, B1, C1, D1 and E1? After substitution and simplification, all the coefficients are different except these two. F and G are remain same. Whatever be the F and G in the given PDE, there is no change in F and G, but all other coefficients are different. That's why we put A1, B1, C1, D1, E1 instead of A, B, C, D, E. Okay, then this is A1. A1 is A into psi x square plus B into psi x psi y plus C into psi y square, etc. B1, C1, D1, E1, etc. like this. Okay, so you by heart all these formulas: A1, B1, C1, D1, E1. Otherwise, you have to find all the partial derivative using chain rule and substitute and simplify. I think it's a very lengthy process. It's a chance of error chance undavada. So better you by heart this formula. Actually, this is the canonical form of the given PDE. So our main task is to find psi and eta. Psi in terms of xy and eta in terms of xy. Okay, then finding this psi x, psi y, eta x, eta y, and substitute everything in A1, B1, C1, D1. Then we find A1, B1, C1, D1, E1 and substitute in this equation, we get the new PDE. So this is the new PDE corresponding to the given PDE, and this is called the canonical form of the PDE. You got it? Okay, so you by heart this formula. So next we are going to discuss a problem. Classify and write the canonical form of uxx minus x square uyy equal to 0. Okay, so by comparing to the standard form, what are the coefficients A, B, C, D, E, F and G? By comparing to the standard form, what is A? Yeah, this is a standard form. I will show you the standard form. Yeah, this is our standard form: A uxx plus B uxy plus C uyy plus D ux plus E uy plus Fu equal to G. This is the standard form of the PDE. So comparing with the standard form, what is our A, B, C, D, E, everything? What about A?
A is
1, B
0
0, C
minus x square
minus x square, then D
0.
Yeah, rest of everything 0. Everything is 0. So first we have to classify this PDE. So to classify this PDE, we have to find the delta, discriminant. What is delta? Delta is nothing. This is b square minus 4ac. So here b square is 0 square minus 4 times a 1 c 4ac. So that is into minus x square. So this is equal to 4x square. So what about this delta? Is it positive or negative or 0? This is 4x square.
Positive.
Yeah, it is positive. It is throughout positive except x equal to 0. Okay, so we remove that case. It's a very particular case when x equal to 0. X equal to 0 means on the y-axis. Okay, x equal to 0 means it's a y-axis. Except y-axis, this PDE is hyperbolic. You got it? Except this y-axis, this PDE is hyperbolic. On the y-axis, what happened? What is the nature of this PDE on the y-axis?
Parabolic.
Yeah, on the y-axis, this PDE is parabolic. Okay. Anyway, we are going to find the canonical form of this PDE except y-axis. Okay. So we are going to find the canonical form of this PDE when it is hyperbolic. So to find the canonical form, first we have to identify two independent reversible functions psi and eta. To find psi and eta, first of all we have to find the characteristic equations. What are the characteristic equations? Characteristic equations is given by the formula dy by dx is equal to b plus or minus square root of delta by 2a. Okay, so what is b? B is here 0 plus or minus square root of 4x square by 2a, that is 2. This is 2x. Okay, this is 2x by 2, that is x. So plus or minus x. So now we have two differential equations, dy by dx is equal to x and dy by dx is equal to minus x. Okay, by solving these two equations we get the characteristics. How to solve this differential equation? You simply integrate, because it's a very simple equation, you can integrate directly. So by integrating this expression, we have the solution y is equal to x square by 2 plus some constant c1, and from this expression we get y is equal to minus x square by 2 plus c2. You got it? And what about this one? From this we get, okay, from this we are rearrange like this, y minus x square by 2 equal to c1, and from this we get y plus x square by 2 equal to c2. Okay, so these are the characteristic of given PDE. Okay, then how to construct psi and eta? If it is hyperbolic, it is very easy. If it is hyperbolic, you can choose psi as this one, this LHS. Okay, so you can convert the given characteristic as a some function of xy equal to constant and some function of xy equal to constant. You choose one function as psi. So I am going to choose this function as psi. There is no order, so you can choose any one of them as psi. So I am going to choose the first one as psi, and the second one as eta, that is y plus x square by 2. This is always possible if the given PDE is hyperbolic, because if it is hyperbolic, we know that there are two real characteristics. Okay, so you can easily find that psi and eta. Psi is nothing, the function of xy except that arbitrary constant. Similarly, eta is nothing, the function of xy except that arbitrary constant. Okay, so we can easily find psi and eta. They are always independent. If it is hyperbolic, this psi and eta are always independent. No need to check they are independent or not. Okay, so now we have psi and eta. Then what is our next procedure? So already we classified it. Then find psi and eta, because it's a hyperbolic case. Okay, if it is hyperbolic, then you can find psi and eta like this. Then we have to compute a1, b1, c1, d1, e1 using this formula. So to compute a1, b1, c1, d1, e1, we have to compute psi x, psi y, psi xx, all the partial derivatives, or we have to find all the partial derivatives of psi and eta. So before moving to evaluating a1 to e1, you simply evaluate psi x, psi y, psi xx, psi xy, and psi yy. Similarly, eta x, etc. etc. What is psi x? What is psi x? What is psi x? Minus x. What is psi y? What is psi y?
1.
And what about psi xx? This one?
Minus 1.
No, 0. And this one? 0. Similarly, you can find all derivatives of eta, and using this formula, you can evaluate a1, b1, c1, d1, and substitute it in this equation. We get the final canonical form. Okay. Only thing is, canonical form should contains only the term psi and eta. Not x and y are allowed. Okay. So after substituting, you should convert everything in terms of psi and eta. Okay. So നിങ്ങൾക്ക് ഒരു ഹോംവർക്ക് ആയിട്ട് ഇരിക്കട്ടെ. അപ്പോൾ നിങ്ങളതൊന്ന് കംപ്ലീറ്റ് ചെയ്യുക കേട്ടോ. You should complete this problem. You remind one thing, after simplification, everything in terms of psi and eta. Okay, ഞാൻ ഫൈനൽ ആൻസർ നിങ്ങളെ കാണിച്ചു തരാം. ഇതാണ് എൻ്റെ ഫൈനൽ ആൻസർ. This is the final answer. ഇങ്ങനെ വരും. After simplification, you get like this. I think after simplification, one term x square is there. You can convert x square using this expression. If you take the, I think, psi minus eta or eta minus I, you get x square in terms of psi and eta, then substitute. That's all. Okay, that's all. Simple. Okay. If any doubt, then please ask me.